One day when I was in college, my friend walked into my room after just returning from a career fair with some free souvenirs, including a toy rubber bouncy ball. And he asked me what might seem to be a simple question. Hey, you're the material scientist. What makes a bouncy ball bouncy? Alright, just put me on the spot, why don't you? Thanks. On the fly, I answered with something like the following. To be bouncy, a material has to be highly elastic. That is, the material can be stretched or compressed, but once the force is released, it will automatically return to its original shape without sustaining any permanent deformation. And any mechanical deformation energy applied to the material will return with minimal loss. The elasticity of rubber comes from its modified polymer structure. The molecular structure of both rubber and polymer plastics consists of lots of long, flexible molecular chains all tangled together like a plate of spaghetti or a ball of Christmas lights. Plastics are not super elastic because these chains can slide past each other when pulled far enough. In a rubber, these molecular chains are strongly bonded or cross-linked together in spots. The chains are flexible and have enough slack that they can be pulled and stretched really far without breaking. And because the chains are anchored by crosslinks, they'll snap back to close to their original position when the force is released. So the molecular structure of a rubber is sort of like a 3D web of connected springs. What's also interesting is that the springiness or elasticity of the chains is entropic in nature and not due to the strength of chemical bonds, at least not until extreme strains and only above the glass transition temperature. In most other materials, their stiffness is based directly on the strength of physical or chemical bonds, but these bonds, while strong, can't be stretched very far before they break entirely. Alright, so maybe I wasn't nearly so cogent when I was a 20-something college student. I think I muttered some of the stuff about crosslinks and entropic chain elasticity. My friend said, okay, perhaps a bit dubious, and left. I don't know if he was satisfied with my answer. As for myself, well, I knew immediately that I was not satisfied. Don't get me wrong, everything I just explained was accurate. The problem was, I hadn't completely answered the question. What I just described was the molecular mechanism of elasticity in a rubber. But I didn't answer why rubber is used for bouncy balls, instead of a different type of elastic solid. Here's the thing. Nearly all solids are elastic within a certain range. Metals, glass, ceramics, plastics, wood, all of them can be elastic. They just have different ranges and levels of elasticity. Here's the same question put another way. If elasticity is necessary for bounciness, and all solids can be elastic, why is rubber used to make toy bouncy balls? Why aren't metal balls also bouncy? The answer to that last question? They can be! Have you ever played with tiny metal ball bearings? Be careful, you could put an eye out. They bounce all over the place. But if you had a metal ball, the same size as a toy rubber ball, you would smash divots into the floor trying to bounce it. What I just said, that's a clue as to the more complete answer to the question, and we'll cover that answer in two parts. 1. How do materials respond to stress or strain? What material properties describe that response? And 2, what happens during the collision, how much energy is involved, and how is that energy distributed? Let's start with a bit of high school physics, specifically Hooke's law for springs, F equals K times X. This equation says that for a simple elastic spring, the spring force F increases linearly with how far the spring is stretched, X. The stiffness of the spring is expressed as the spring constant K, the slope of the line. The elastic properties of materials is described in a similar way. Imagine a solid rod of some material with a set length L and cross-sectional area A. If we apply a force to it, it will extend some distance dl. However, instead of force, we plot force divided by cross-sectional area, which we call stress. Instead of extension, we consider extension divided by initial length, which we call strain. The response of a material to deformation can be plotted out on a stress-strain curve that might look something like this. apply this amount of stress, and this is how far the element will stretch as a percentage of original length. Now, stress-strain curves come in all sorts of shapes and sizes, but a lot of intrinsic mechanical properties of a material are quantitatively defined on this one curve. This straight segment is the linear elastic regime, where the material acts like a simple spring and can be bent or stretched without incurring any permanent deformation. The slope of the line is the tensile modulus or Young's modulus. This is analogous to the stiffness or the spring constant of a simple spring. The higher the modulus, the steeper the slope, the stiffer the material. The inverse or opposite of stiffness is compliance or flexibility. A quick aside, in an engineering context, the terminology is specific. The words stiffness, toughness, and strength refer to very specific quantities and can't be used interchangeably. Even terms modulus and stiffness are technically different in a certain context. I will mostly try to adhere to the proper engineering usage, but please excuse any colloquial slips I might miss. Now, one thing I didn't specify in that whole rambling introduction is that elasticity has a limit. All solids are elastic, but only up to a certain maximum deformation. Stretch any material far enough, and it will sustain damage or break completely. That's where the rest of the stress-strain curve comes in. Draw a parallel line to the elastic line offset by 0.2% strain. Where the curve and line intersect, that's the yield strength, the maximum stress the material can support before beginning to incur significant permanent damage, and a commonly used point delineating the end of the linear elastic range. The rest of the curve is the plastic deformation regime. Let me quickly emphasize for those less familiar with the vocabulary, the term plastic here does not refer to the solid materials your soda bottles and grocery bags are made of. It refers to plasticity, or the ability of something to be shaped or molded. Stretch an element out to here, release the force, and it will recover somewhat, but there will be some permanent deformation. Stretch the material far enough, and it will fracture. The curve terminates. Ductility is described as the amount of plastic strain sustained up to fracture. A material that is brittle, like glass, may have almost no room for plastic deformation before fracturing, whereas a material that is ductile has a broad plastic deformation regime. The highest point on this curve, that's the ultimate strength, or the maximum stress an element can withstand without breaking. The area underneath the curve measures the strain energy, or energy of deformation, the amount of energy per volume needed to deform the material up to that point. Resilience is the stored elastic strain energy at the yield strength, calculated from the area underneath the elastic portion of the curve. Toughness is the total strain energy required to rupture the material, calculated from the area underneath the whole curve. Note that a brittle material may require a substantial initial force to break, but it doesn't absorb much energy when it fractures. It has low toughness. Finally, hardness is defined as... Alright, so not every term has a singular quantitative definition. I know, this is a lot to take in all at once. If you didn't catch all of that the first time, don't feel bad. You can do a quick search and you'll find plenty of other videos worth watching that cover these topics in smaller, more manageable chunks. Or you could rewatch this one. I don't mind, really. And for the purposes of this video alone, you only need to get a handle on the elastic mechanical properties. These are modulus, yield strength, and resilience. These properties have to be considered for both ball and surface. A ball striking a surface is a collision, and collisions, especially inelastic ones, can be messy, chaotic affairs. Luckily, we're only concerned with elastic collisions, which are much simpler and which we will grossly oversimplify even further. However, even with this oversimplified model, the qualitative conclusions we draw will still be sound. When a bouncy ball collides elastically with a surface, we can imagine it as if a perfect spring is running head-on into another spring. The elasticity of each spring depends on the mechanical properties of the materials as well as the geometry of the objects. Although, let's table the discussion about geometry for now. There are 3 important points to consider about the scenario. 1. When 2 or more springs are squeezed together in series, the force or stress on them is equal. 2. At some point in a perfectly elastic head-on collision, the speed of the ball is 0, which means that, at that point, all of the initial kinetic energy of the ball must become stored as elastic strain energy in both the ball and the surface. 3. If at any point the stress of the collision exceeds the yield strength of either material, or if the strain energy exceeds the resilience of either material, then the material sustains damage and the collision becomes inelastic. With those points in mind, let's draw up some hypothetical stress-strain curves and imagine what happens when one material collides into another. During the collision, due to the equal force rule, we write up both stress-strain curves at a similar stress. But how far do we need to write up the curves? That is determined by the second rule, by how much kinetic energy needs to be stored as strain energy. The amount of stored energy is the total area underneath both curves. At the point of 0 speed, for the collision to remain elastic, that sum has to equal the initial kinetic energy of the ball without exceeding the yield strength of either material. If the yield strength or resilience is exceeded, then the energy gets dissipated as heat or broken bonds during plastic deformation, and the collision becomes inelastic. Here you can see that in a collision between a rigid material and a flexible material, the flexible material will typically be the loser. The flexible material gets more compressed, and it must absorb more of the collision energy. Another important thing to notice is that if both materials are stiff, the collision will be more forceful than if they're both flexible. Rigid materials are not good at absorbing impacts. This is why, for example, a heavy rain is inconvenient, but a hailstorm is destructive or even deadly. Finally, regardless of stiffness, it's the material with the lower yield strength that will fail first. Baseballs are softer than glass, but they can still break a window. The mass or size of the projectile does not affect the mechanical properties, modulus and yield strength, but it does determine the collision energy, and mass scales as radius cubed, whereas the contact area scales as radius squared. That's why small metal ball bearings will bounce all over the place, while larger metal balls will damage themselves or whatever they hit. Lower density will reduce the mass of the object for the same contact area, and thus will also make it bouncier. So these are the reasons that rubber is used for toy bouncy balls. 1. Rubber has low density, and less mass per volume means reduced collision energy and contact stress. 2. Rubber has low stiffness, further reducing contact stress upon collision. 3. Rubber has relatively good resilience and yield strength, meaning it can absorb and release a substantial amount of collision energy elastically without breaking. 4. One last caveat is that the surface you bounce the ball off of also has to have sufficient yield strength to support the elastic collision. And that, my dear friend from college, is why bouncy balls are bouncy. I'm not going to comment on how many years that answer wasn't coming. Actually, I'm not done just yet. I found this explanatory framework to be useful in shedding some light on a couple other fun stories about collisions. So I'm going to talk about launching poultry at hundreds of miles per hour and about the liberal application of freedom to tanks. But first, a quick note about geometry. Geometry of the colliding objects is a very important consideration because it determines the overall stiffness of both elements and it affects how the collision force is applied or distributed. Remember, the material properties are measured from stress curves, that is, force per area. Sharpen the projectile to a point, and the reduced area of contact increases the stress and the chance of material failure, resulting in the projectile piercing the surface. Conversely, hollowing out the ball into a spherical shell reduces both the mass of the projectile and changes how strain is distributed. This would be like a table tennis ball, or a wiffle ball, or those hollow plastic ball pit balls in play places. You know, for kids. A solid ball of the same plastic would not be as bouncy. There are a bunch of other geometric and structural variables like angle of incidence, panel thickness, porosity, internal or external reinforcement, yada yada yada, you get the picture. Certain parts of planes and helicopters, like engines and canopies, are designed and tested for resistance to collisions with birds, or bird strikes, at reasonably expected speeds. This is done using a chicken cannon, an air cannon used to launch raw poultry, or simulants of clay and plastic, at vehicle parts at upwards of 400 miles per hour. There is a common legend, possibly apocryphal, hard documentation is scant and details vary from telling to telling, that some organization was performing this test themselves for the first time, and they were astonished at the carnage and destruction wrought by their poultry projectiles, even when the targets were reasonably expected to survive. So the engineers sought some advice as to what they might be doing wrong. They received a four-word reply: "Gentlemen, thaw your chickens." This story was actually tested by the Mythbusters, and I remember Adam Savage expressing skepticism because, he reasoned, a frozen chicken has the same kinetic energy as a thawed chicken. The story would later be deemed plausible when a frozen chicken that they fired from their own cannon punched straight through multiple panes of solid glass in spectacular fashion. Although the legend may be apocryphal, I still think this is a fun story. And it's also instructive to go through the flaw in Adam's logic. Remember, it's not just about kinetic energy, but how that energy is distributed during the collision based on stiffness and strength. Try it for yourself. Sketch what you would guess to be the stress-strain curves for raw poultry versus frozen poultry. The modulus and yield strength of raw meat are low, and try not to think too hard about what that implies about the squishiness of the human body. Ice is stiff and brittle, but frozen meat is probably much tougher without being much more compliant. In a collision with a plexiglass windshield, raw meat would deform more, absorb more collision energy, and fail first in a very messy way. Frozen meat being stiffer results in much higher collision force and contact stress, and therefore a greater chance that the plexiglass or whatever the target of the ice chicken's ire will lose. Once again, although the kinetic energy is the same in both cases, it is how that energy is distributed that matters. The softer a material is relative to its opponent, the greater the share of the collision energy it receives in the exchange. Depleted uranium is what is left after processing of uranium metal to remove most of the radioactive atoms for use in more impactful applications. It can still be chemically toxic as a heavy metal like lead or cadmium, but its radioactivity is reduced to 60% that of natural uranium. But I'm not here to talk about radiological or chemical safety. I'm here to talk about the most lethal form of depleted uranium available today. 1 pound chunks of it traveling towards you at 1,000 meters per second. One of the reasons uranium is used in armor-piercing munitions is its density, which means a projectile of it has more momentum and is able to focus that kinetic energy onto a smaller area. More mass in a compact space also means a straighter trajectory, less susceptible to air resistance, which is exemplified in something called the ballistic coefficient. The high temperatures generated on impact will also cause uranium fragments to burn, which then has a chance to ignite fuel or detonate munitions. And at first, I thought I'd be able to point to the mechanical properties of uranium like hardness or yield strength and further explain its armor penetration ability. But the story is not so straightforward. The mechanical properties of both steel and uranium can vary widely depending on the specifics of alloying, heat treatment, and working. Instead, I learned about a phenomenon called adiabatic shear banding. When impacting a hard surface at high speed, many metals mushroom out, distributing the plastic deformation energy throughout the volume of the slug, increasing the contact area and reducing the penetrating power. In uranium and certain metal alloys, plastic strain gets concentrated in thin planes called shear bands. With rapid strain rates, the heat from shearing the material doesn't have time to dissipate, so the shear band heats up, and local thermal softening exacerbates shear banding. Thus, upon impact, instead of mushrooming out, slices of the bullet shear off while it maintains its penetrating point. Understanding adiabatic shear banding is important not just for ballistics, but also manufacturing and machining of certain alloys. And there's still some research on the finer points of the phenomenon, like dynamic recrystallization and grain rotation. Alright, so this part might not be so relevant to toy bouncy balls, but it demonstrates one of the reasons I've come to appreciate the original question of why bouncy balls are bouncy. It's a deceptively simple question with a more complex answer that can serve as both an accessible introduction to the field of mechanics of materials, as well as a gateway to exploring a number of fascinating rabbit holes. Everything I covered in part 1 can be found in an introductory college course on mechanics of materials, but if you dig deeper into the mechanics of impacts, you might encounter adiabatic shear banding, or chicken cannons. I mean, even at the beginning of the video, I just blithely introduced entropic chain elasticity in plastics and rubbers, and I didn't even cover nonlinear elasticity, or coefficient of restitution. There's also another corollary question I didn't touch on. How can rubber be used for bouncy balls, but also for vibration dampeners and shock absorbers? Wouldn't you expect elasticity to not be conducive to dampening functions? Delving into that question leads you to even more topics, like different formulations of rubber, dynamic mechanical properties, glass transition, viscoelasticity, anelasticity, and hysteresis. Sometimes the best questions are the ones that lead to more questions.